So welcome to week 7 tutorial for the course Basic Linear Algebra taught by Professor Inder Kumar Rana. I'm Pintu Kumar. I'm a PhD scholar at IUIT Bombay. So today what I plan to cover is, first of all, I'll try to cover some of the some examples based on Gram-Schmidt's process. I covered it last time, but I think because of lack of time I rushed a bit. So I'll try to cover some more examples based on it. And then I'll try to solve some problems today based on eigenvalues, eigenvector, integration, and inner product. So these are going to be very basic questions because the course is almost about to end and might be helpful for you from examination perspective. So these are going to be very basic problems just to clear your very basics if it is not clear yet. Okay. So beginning with Gram-Schmidt's process. So if you recall, Gram-Schmidt's process is a method to convert your linearly independent vectors to orthogonal vectors. Okay. What are orthogonal vectors? You can see orthogonal vectors as perpendicular vectors or vectors whose inner product is equal to 0. Okay. So this is our goal that we want to do. So in order to do, what we do is, so let's say you have a linearly independent vectors w1, w2, wn. You want to convert them to your orthogonal vectors v1 to vn. So what you do is you assign the first vector as the first vector from your linearly independent set. Okay, so this is orthogonal set that you are constructing, and this is your linearly independent set on this side. Okay. The next thing that you do is, in order to define your v2, I would say, what you do is you from existing w2 you subtract that is the projection of w2 onto v1. Okay. So what we are subtracting, this term denotes the projection of w2 on v1. So what we are doing is actually we are subtracting any component that is in the direction of v1. Then whatever we will obtain, this v2 would be perpendicular to v1, and hence we will get one more element in our orthogonal set. Similarly, here is a formula for vk. So in order to convert vk, from wk you will subtract the projection of wk on all of v1, v2 till vk minus 1. So v1, v2 till vk minus 1. Okay, last time I did an example. I'll do one more so that it is much more clear how do we approach this kind of problem. Okay, so here one more thing, we are being asked to find an orthonormal basis, not an orthogonal basis. Okay, so orthonormal basis is nothing. So this is a orthogonal set plus vectors with norm equal to 1. Okay. Okay. So what we will do is we will first convert this to orthogonal set, and then for every vectors that we obtain in the orthogonal set, we'll make their norm as 1 by dividing it by their norm. Okay. So as per the process, so there is a change in notation. This example using v1, v2, v3 as the original vectors, your Li vectors, and now w1, w2, and w3 will be your orthogonal vectors. Okay. So as per the method or the process, the first vector is same as the first vector from the linearly independent set. So your w1 is nothing but v1. So this becomes 1, 1, 1, 1. Okay. So your first vector is very conveniently your v1 only. Okay. Now, in order to obtain w2, as per the instruction, what we need to do is from v2, we need to subtract projection of v2 onto w1. Okay. This is the formula that we have, right? So we have, let's write it out. Okay. So let's write it here only. So this is your V2 is given to be minus 1, 4, 4, minus 1. Okay. Now, if you calculate the dot product between V2 and W1, so you have V2 and W1 is this, so this is minus 1. Okay, so let's calculate this. This is minus 1 plus 4 plus 4 minus 1. Okay. And it would be divided by the norm of W1. So norm of W1 is nothing but 4, norm of 1 square, okay, norm of W1 square. And this is multiplied by 1, 1, 1, 1. Okay, what do we get? We get 1, 4, 4 minus 1. And this is 6 by 4, that is your 3 by 2. Okay, so what do we obtain? So you obtain, so this is minus 1 minus 3 by 2. You get minus 5 by 2. Your second component is 4 minus 3 by 2. So this is 7 by 2, 7 by 2. Sorry, this is 3. Sorry. So this would be again 5 by 2, 5 by 2, and minus 5 by 2. Right. So this is the second element of our orthogonal set that we have obtained. Okay. Now, similarly, we need to obtain the third element also. So your W3 is V3 minus projection of V3 onto W1 minus projection of V3 onto W2. Okay. So if you write this out and we'll solve this, so this is 4 minus 2 to 0. So this is 4 minus 2 to 0. Okay. And you have W1 and W2 that you have obtained over here. Okay. So this is, now if you take the dot product of V3 with W1, so we are taking this V3 with W1, and this term is, so you have 4 minus 2, this would be 4 over here, and the denominator is also 4. This is 1, 1, 1, 1. Okay. And then you have to subtract. Now you need to take dot product of these two things, right? So dot product of this quantity and this vector, okay, that you will calculate over here. And this particular vector is, so this minus 2 and minus 2 would lead to 0. The last term is already 0. So you will get contribution only from the first term, and that would be minus 10, right? And divided by this norm of this thing. So what is norm of this thing? This is 25 by 4 into 4, that is 25. So norm would be square root of 25, but if you take norm square, you will get as 25, right? And this is some 5 by 2 times minus 1, 1, 1 minus 1. So what do you obtain? So you can further cancel it out. So this is 5, okay, and you can cancel it out as minus 2, okay, and this becomes minus 1, right? So just write it out neatly. What we will obtain is 4 minus 2 to 0 minus 1 time 1, 1, 1, 1 plus 1 times minus 1, 1, 1 minus 1. What you obtain? 4 minus 1 is 3. minus 1 again is 2. So minus 2 minus 1 is minus 3 and plus 1 is minus 2, right? 2 minus 1 is 1, plus 1 is 2, okay? And the last term is minus 1, this is minus 2, okay? So what you have obtained, so you have obtained W1 as 1, 1, 1, 1, W2 as minus 5 by 2, 5 by 2, 5 by 2, and again minus 5 by 2, and W3 as 2 minus 2, 2 minus 2, okay? So now what I want you to do is just verify quickly that these vectors are indeed orthogonal to each other, right? So if you take this dot product, you can see that all the terms over here is 1. So
Hello,
yes, hello,
hello.
hello.
Sir, please scroll a screen up to down.
What are you saying?
Uh,
Mm-hmm. Am I audible to you?
yeah.
You want to ask something?
Sir, scrolling up to down first question.
Uh, Actually, you are not very clearly audible, but I hope you are asking me to scroll to the question. So in the question, what we were given is that you have
Yeah.
some set of vectors and you need to
Sir,
find.
clear.
Okay.
Hello.
Hello.
Yeah, sir, clear.
Okay.
Please move next.
Yeah. So, okay. So one thing over here that is left is you need to convert these vectors to orthonormal vectors.
Yeah.
Okay. So whatever vectors that you obtain are orthogonal. Now, how will you move to orthogonal vectors? So let's call our orthogonal vectors as O1. So O1 is nothing but W1 divided by norm of W1. Okay. So what is norm of W1? Norm of W1 would be square root of 4. So that is 2. So this is half times 1, 1, 1, 1. So this is 1 by 2, 1 by 2, 1 by 2, 1 by 2. Okay. And similarly, you can obtain O2 as your minus 1 by 2. So we calculated the norm square of W2, right? That was 25. So what is norm? Norm is, yeah, hello. Norm is 5, so you'll obtain something like this. Again, for this case, you can again find this is 4 into 4, that is 16. So norm of W3 square is 16, or the norm is 2, so you can obtain half minus half, half minus half. So now
Sir,
when
what
you,
is theta?
what is?
What is theta here?
So this is not theta. I'm using O1 to denote my first orthonormal
Okay.
vector. Okay.
Okay.
Okay. So now, like if you look at these two set of
Sir,
vectors,
but why use V1 in 1 by 2 into V1?
okay. So in question, we were asked that we have to find an orthonormal basis, not a orthogonal.
Yeah.
Okay. So
Okay.
how we
Then
how,
we multiply 1 by 2 in given
ha,
vector.
so what we do is, let's say you have W1.
If we find out orthonormal, then we must multiply 1 by 2 in given vector.
No, no, you should not multiply always by 1 by 2. I'm telling you what you should do. So if you have W1, W2, W3, let's say 3 orthogonal, first you will obtain orthogonal vectors when you are asked to obtain orthonormal, okay?
Okay.
Then for W1, you will divide it by its norm,
Yes.
okay? So in this case,
Yes.
norm was 2. So dividing by 2 is same as multiplying by 1 by 2. That's why I multiplied by 1 by 2. in this case, if you look at W2, its norm was 5. Okay, that's why
But why multiply by 1 by 2?
we divided by its norm. Okay, so I'll tell you why we do this. So what is what is a normal vector?
Oh, sir, okay.
I'll tell you.
That means the formula of unity vector, yeah.
Yeah. So normal vector is something like a vector
Oh,
with length 1, right?
yeah.
So let's say you have a vector like this, which is, let's say, 2 comma 2. Okay, so it has some length.
Yes.
So if you want to find a vector in same direction but with length 1, right? So what you do is you take this vector and divide it by its length. So like if you divide
Yes.
any vector by some scalar, then its direction won't change, right? So if you have a vector, let's say v, and you multiply it by a scalar or you divide it by a scalar, then its direction won't change, right? Only the
Okay.
length of the vector changes.
Yes.
So same thing we are doing over here. So we obtained 3 vectors which are perpendicular to each other. Now what we want is that they should also be of unit length. Okay. So then we are calculating its length. Norm is nothing but the length of that vector. Okay. And then we are dividing by that length.
Given by vector mod of this.
Mod of W represents length of the vector.
Yes.
Okay. So yeah, so in this case the length came out to be 2, so we divided by 2. In this case the length came out to be 5, we
Okay.
divided by 5. Here it came out to be 4, so we divided by 4. Now is it clear? Okay. So one thing that I want to mention is, let's say I have some W1, W2. Now if you look at these vectors and you want to somehow sort of look at it or compare it in some way. So over here, all the entries are ones. Here you have something to the scale of -5 by 2 and 2. So they don't look very comparable to each other, right? But when you find sort of orthonormal vectors, then you can straight away see that these vectors only have changes in sign at some place. So what I feel is that this orthonormal vectors also sort of becomes more interpretable to us, like when we are using it for some application or those kind of things. Okay. Okay. So that example is over. And we'll try to do one more problem on this Gram-Schmitt's orthogonalization process. Okay. So what we will try to do is, this is a sort of slightly non-trivial as compared to the previous example. Now over here, the vector space that we are talking about is no more R3, but P2R. By now, I hope that you know what is P2R. It is polynomial up to degree 2. So elements of form 1 plus x square or x square minus x. These kind of elements are vector in this particular vector space. Okay. And also they are saying that we should use standard ordered basis for beta. Okay. So first of all, beta for P2R is 1 comma x square. Okay. Now they are asking us to do, so let's call this as U1, this as U2, and this as U3. Then they want us to convert this U1, U2, U3 into an orthogonal basis, V1, V2, V3. Okay. And then use this normalization thing to convert them to an orthonormal basis. Okay. We will do all these steps. Okay. Now, as I told you, when we begin with Gram-Schmidt's process, so I am requesting, like, whoever has joined, this is probably the last example on Gram-Schmidt's process, and this is a sort of important topic in linear algebra. So at any point, if you don't understand anything, please feel free to interrupt me as many number of times as you want. Okay. Okay. So the first thing that we should do is that we should take the first vector same as the first vector of our existing basis. This is what Gram-Schmidt's process said, that my V1 is equal to U1. Okay. Now we need to find V2. Okay. What is V2? V2 is U2 minus V2 U1 norm of U1 square into U1. Okay, this is what we want to find. Now we have a certain definition for dot product given over here. So this is not a standard dot product that we do in case of Rn, but this is integration of this thing from -1 to 1. Okay. So what it is, so U2 is what it is, x minus, now let's okay, first of all, let's calculate this V2 comma U1. Okay, so what it is, this is -1 to 1. What is V2? V2 is x. So we will write it in function of t. So x becomes t. Okay, and your U1 is nothing but 1. Okay, so this becomes 1 dt. So what it is, t square by 2 from 1 to -1. So this is 1 by 2. Okay, minus 1 by 2. Okay, what it is, I hope I'm not doing any mistake over here. Yeah, this is -1 to 1. So this came out to be very clean. Okay, so this is 0, right? So t square by 2, if you put in 1, this is 1 by 2 and minus 1 by 2. So this is 0. So if my dot product came out to be 0, then I need not worry about other components over here. So my V2 is nothing, U2 minus 0 times of U1 divided by norm of U1, which is U2 itself. Okay, so what we obtained U2 as? We obtained U2 as x only. Hope that this is not the case in third one. Otherwise, this example won't be. Okay, so now V3 is U3 minus projection of, here I have made a slight mistake. Here I should write U2 on V1 and this should be V1. But the calculation remains same. That is just a notational mistake that I did. Okay. Okay. So this is now U3 is projection on V1 divided by V1 norm into V1. Okay. Minus U3 is projection on V2 divided by V2 norm into V2. Okay. We'll first try to find out these dot products that we have and then we'll proceed. So what is U3 V1? Okay, now my U3 is x square. Okay, so this is integration -1 to 1 t square into 1, right, dt. What it is? This is t cube by 3 from 1 to -1. So this is 1 by 3 plus 1 by 3. So this would have been minus of -1 by 3. So this is nothing but 2 by 3. Okay. Let's calculate this quantity also. That is my V1 square, that is V1, V1. Now V1 is just 1 comma 1 dt -1 to 1. So this is t from 1 to -1. So this is 1 minus of -1, which is 2. Okay. If I make any calculation mistake, please let me know. And then, so we are done with the first term that we need to evaluate. Okay. Now we'll come to the second thing. So the second thing is this
Hello.
is hello.
Sir, repeat again.
What?
Sir, repeat again.
Your voice is not very clear. Can you just type in the chat box? I'll. I'm waiting for your chat. Hello, I'm waiting for whatever doubt you have. Okay, I'll repeat it. I'll try to go step by step, and please, again, like if you have any doubt, please stop me. Okay. I think I have I'll just go for a simpler example and then I'll come back to this one. I think I have one example. Yeah. Okay. Let's try to do this example first, then we'll go back to that. Okay. See, first thing that you should remember is what is the use of this Gram-Schmidt's orthogonalization process, right? So what is its use? Okay. So first thing, like if you are given with some linearly independent set, okay, then it is used to convert it to orthogonal set.
हेलो
Hello.
और सर ये क्वेश्चन है मुझे वो
हाँ
कॉन्सेप्ट ही समझना फिर से
हाँ, उस पे पहुंचेंगे, पर नॉर्मल वेक्टर्स के लिए समझ गए अच्छे से
हेलो
कैसे करना है। हेलो,
हेलो
आवाज आ रही है?
हेलो
एम आई ऑडिबल?
हेलो
हेलो।
यस सर
हाँ, मैं
यस
बोल रहा
सर
हूँ कि
मैं बोल रही थी कि ये क्वेश्चन तो मैं कर लूंगी बस वो जो कॉन्सेप्ट दिया था उसको वही मेरे को समझना फिर से एक बार
वो ठीक है, पर मैं पूछ रहा
हेलो
हूँ कि नॉर्मल वेक्टर्स के लिए समझ गया तुम्हें, वो हो जाएगा।
यस सर
ठीक है, तो चलते हैं उसी क्वेश्चन पे। ठीक है, अब इस क्वेश्चन में क्या था, एक बारी क्वेश्चन पढ़ो
यस
पहले।
सर
1 मिनट लेके क्वेश्चन पढ़ो, फिर मैं बताता हूँ।
let v equal to p or r with the inner product f of x into gx equal to integration -1 to 1 f of t g of t dt and consider the space p2 over r with the standard order basis beta. We use the Gram Schmidt process to replace beta by an orthogonal basis u1 u2 u3 4 p2 over r and then use this orthogonal basis to obtain an orthogonal basis for p2 of r.
ठीक है, तो हमें करना क्या है, अब हम लोगों ने जो वेक्टर्स के लिए अभी ग्राम स्मिथ प्रोसेस लगाया था, तो दैट वाज आवर आर एन स्पेस, राइट? ठीक है, उसमें वेक्टर्स थे हमारे पास।
Yes,
पर
sir.
नाउ व्हाट वेक्टर स्पेस वी हैव इज पी टू आर। ठीक है, पी टू आर क्या होता है? पॉलिनोमियल्स अप टू डिग्री 2। ठीक है, so you know what are polynomials, right? Like expression of this form,
Yes, sir.
1 plus x 1 plus x square। तो कोई भी पॉलिनोमियल
Yeah.
जिसकी डिग्री 2 तक हो, नेगेटिव डिग्री वाले पॉलिनोमियल्स हम नहीं लेंगे, स्टार्टिंग फ्रॉम डिग्री 0 पॉलिनोमियल दैट इज 1 अप टू डिग्री 2 पॉलिनोमियल, अगर उनका एक सेट बनाते हैं हम लोग, तो दैट फॉर्म्स अ वेक्टर स्पेस। ओके, वी नो दिस, वी हैव प्रूव्ड दिस इन पास्ट। ओके, सो दिस इज पॉलिनोमियल अप टू डिग्री
Okay.
2। अब जब हम लोग ग्राम्स, इसका कुछ ना कुछ बेसिस होना चाहिए पहले, या फिर कुछ लीनियरली इंडिपेंडेंट सेट होना चाहिए जिसको हम लोग कन्वर्ट करेंगे यूजिंग ग्राम स्मिथ प्रोसेस। ठीक है, तो वो सेट इन्होंने बोला है कि यू टेक इट एज स्टैंडर्ड बेसिस, ठीक है। तो स्टैंडर्ड बेसिस इसके लिए होता है 1, x और x स्क्वायर, ये 3 एलिमेंट होते हैं, ये वेक्टर
yes,
साइज वेक्टर स्पेस के, ठीक है। अब अगर हम लोग ग्राम स्मिथ प्रोसेस के इसको देखें, प्रोसेस को देखें, तो इसमें एक ये इनर प्रोडक्ट भी है ना फॉर्मूले में। तो अब हमारे पास वेक्टर है, उसका एक बेसिस है और लीनियरली इंडिपेंडेंट सेट है, एक डेफिनेशन उसकी भी चाहिए हमें कि हम लोग इनर प्रोडक्ट कौन सा यूज करें। So when we go to this function spaces or polynomial spaces, we have many choices of inner products. Okay. तो इन्होंने बोला है कि
yes.
what inner product you should use is this inner product, that is integration from -1 to 1 f to ft into gt. This is the inner product between f and g. ठीक है। So this is the inner product between f and g. और इन्होंने फिर बोला है कि using this information we have to find a orthogonal vector space, sorry orthogonal basis, और फिर उस ऑर्थोगोनल बेसिस को कन्वर्ट करना है ऑर्थोनॉर्मल में, ठीक है।
Orthogonal.
हाँ, सो दिस इज द क्वेश्चन दैट वी आर ट्राइंग टू सॉल्व, ठीक है। अब आते हैं क्वेश्चन पे, इसको रब कर देते हैं। एक सेकंड। हम्म तो अब हम लोग जब ग्राम स्मिथ प्रोसेस की बात करते हैं, तो हम व्हाट इज आवर फर्स्ट स्टेप? First step is to find your v1. So this is not u1, this is v1, v2 and v3 that they have written, ठीक है। So what is v1? You take, और इसको हम लोग नाम दे देते हैं
Okay.
u1, u2 और u3। तो v1 क्या होगा? v1 हो जाता है हमारा हमेशा u1, ठीक है, क्योंकि v1 में हमें कुछ करने की जरूरत नहीं पड़ती है। v1 हो जाता है एज इट इज u1, क्या हो जाएगा ये 1। दिस इज क्लियर, ठीक
Yes,
है।
sir.
नाउ वी विल गो टू u2। ओके, व्हाट इज u2? u2 is based on this gram Schmidt formula whatever we have. What is u2? u2 is,
V1
सॉरी
minus
सॉरी सॉरी, नोटेशन मैं खराब कर दे रहा हूँ। दिस इज v2, ठीक है। व्हाट वी आर ट्राइंग टू फाइंड इज v1 v2 v3, ठीक है। और हमारे पास है क्या? u1 u2 u3। तो दिस इज u2 माइनस ये u है, ठीक है। u2 माइनस u2 का इनर प्रोडक्ट v1 के साथ,
U2 U. Yes, sir. Y V1 comma square into V1.
ठीक है। अब हम लोग को ये फाइंड करना है, ठीक है। इसको फाइंड करने के लिए हमें क्या क्या कैलकुलेट करना पड़ेगा? जब हमारे पास नॉर्मल रियल
Yes,
वेक्टर्स थे, देन वी यूज टू फाइंड द डॉट प्रोडक्ट वेरी इजली, ठीक है। वो डॉट प्रोडक्ट ही था, मल्टीप्लाई कर लेते थे माइंड में ही। पर अभी हमें ये कैलकुलेट करना पड़ेगा यूजिंग दिस इनर प्रोडक्ट फार्मूला दैट वी आर गिवन, और नीचे वाला क्वांटिटी भी कैलकुलेट
yes,
करना
sir.
पड़ेगा। सो दिस इज व्हाट वी विल डू फर्स्ट, ठीक है। तो फर्स्ट ऑफ ऑल लेट्स ट्राई टू कैलकुलेट u2 v1, ठीक है। ये क्या होगा? -1 से 1 इंटीग्रेशन, u2 क्या है हमारा?
Yes,
u2
sir.
इज एक्स स्क्वायर, तो एक्स स्क्वायर की जगह यहाँ क्या लिख देंगे? टी स्क्वायर, ठीक है। अब v1 क्या है?
Oh,
1,
the one.
सॉरी u2 हमारा x है, सॉरी यहाँ पे एक्स स्क्वायर नहीं x होगा, ठीक है। तो t इंटू वन टी टी, ये क्या हो जाएगा? टी स्क्वायर, कहाँ से कहाँ तक? -1 to 1, ठीक है।
Minus
तो
1.
ठीक है, तो इसकी वैल्यू क्या आ जाएगी? 1/2 -1/2 विच इज 0, ठीक। ये बस सिंपल इंटीग्रेशन है। तो क्योंकि ये वाला टर्म हम लोग का 0 आ गया, तो हम लोग बाकी कुछ कैलकुलेट नहीं कर रहे हैं, ठीक है, क्योंकि वो ओवरऑल 0 ही हो जाएगा जब 0 से मल्टीप्लाई हो जा रहा है। तो v2 हमारा क्या आ गया? v2 आ गया u2 माइनस 0 टाइम्स v1 विच इज जस्ट u2। u2 क्या आ गया? x। दिस मच इज क्लियर,
Yes, sir.
ठीक है। अब आगे चलते हैं, ठीक है। अब v3 निकालना है हम लोगों को। v3 में भी सेम काम करेंगे, u3 माइनस उसका प्रोजेक्शन v1 पे, है ना, माइनस फिर u3
Yes,
उसका प्रोजेक्शन v2 पे। अब यहाँ पे हमें चार चीजें कैलकुलेट करनी है, ये करना है, ये करना है, ये करना है और ये करना है, देन वी विल पुट इट इन दिस फार्मूला एंड कैलकुलेट। ठीक है, अब हम लोग जब u3 कॉमा v1 निकालेंगे, सो व्हाट इज u3? u3 इज एक्स स्क्वायर, तो टी स्क्वायर इंटू वन, इसका इंटीग्रेशन आ गया टी क्यूब बाई थ्री। ठीक है, उसको वन से माइनस वन तक करेंगे तो दिस इज वन बाई थ्री माइनस ऑफ माइनस वन बाई थ्री, तो ये आ गया टू बाई थ्री। और अब नॉर्म ऑफ वी वन स्क्वायर निकालना है हम लोग को, तो वो क्या होता है नॉर्म ऑफ वी वन स्क्वायर? दिस इज जस्ट वी वन इनर प्रोडक्ट विद वी वन, राइट? सो दिस इज वन इंटू वन विच इज टू फॉर अस। कूल, ये दोनों चीजें निकाल लिए। नाउ वी ऑल्सो नीड टू कैलकुलेट यू थ्री कॉमा वी टू। ठीक है, अब यू थ्री क्या था हम लोग का? दिस इज माइनस वन टू वन टी स्क्वायर इंटू टी, ठीक है, डी टी। तो ये क्या हो जाएगा? टी टू द पावर फोर बाई फोर माइनस वन से वन, ये फिर से जीरो आ गया। ठीक है, तो अगेन वी नीड नॉट वरी अबाउट दिस टर्म। ठीक है, तो व्हाट इज नाउ माई वी थ्री? वी थ्री इज यू थ्री, लेट्स यूज अ डिफरेंट कलर। वी थ्री इज यू थ्री माइनस, दिस इज टू बाई थ्री, राइट? टू बाई थ्री डिवाइडेड बाई टू टाइम्स वी वन, वी वन इज एक्स, सॉरी वी वन इज वन।
सर,
हाँ बोलो।
एग्जाम में इससे रिलेटेड क्वेश्चन आएंगे?
अब एग्ज़ाम का पेपर का बिल्कुल वो आइडिया नहीं है मेरे को कैसा सेट होगा, पर ग्राम स्मिथ प्रोसेस सर ने भी कराया है कोर्स में और इम्पोर्टेंट भी है, तो आ सकता है। शायद पॉलिनोमियल्स के ऊपर ना है, मतलब थोड़ा कैलकुलेशन मुश्किल हो जाएगा, पर आ सकता है।
Yes.
ठीक है, और लास्ट टर्म हमारा ज़ीरो हो गया। ठीक है, तो व्हाट इज़ यू थ्री? यू थ्री इज़ नथिंग बट एक्स स्क्वायर माइनस वन बाई थ्री। दिस इज, या दिस इज वन बाई थ्री, right? So we obtained our orthogonal basis. What is the orthogonal basis that we obtained? Orthogonal basis was v1 as 1, v2 as x, and v3 as x square minus 1 by 3. Okay, this is the orthogonal, this is orthogonal basis. अब how to convert this to orthonormal?
V1 by mod V1, V2 mod V2,
हाँ,
V3 mod
so
V3.
let's call it O1, तो क्या हो जाएगा वो? v1 by norm of v1. So
Yes.
हम लोगों ने norm of v1 ऑलरेडी कैलकुलेट किया था, it was 2, right? दिस इज नॉर्म पी वन स्क्वायर, तो ये क्या हो जाएगा? ये हो जाएगा वन बाय स्क्वायर रूट ऑफ टू। ठीक, सिमिलरली ओ टू के लिए हम लोग कैलकुलेट कर लेंगे वी टू बाय नॉर्म वी टू, तो क्या हो जाएगा इसका? दिस वुड बी इंटीग्रेशन ऑफ माइनस वन टू वन टी स्क्वायर डी टी।
सर V1 का
बोलो।
V1 का mod 2 कहाँ से आया?
हम लोगों ने कैलकुलेट किया था ना वी वन का नॉर्म। वी वन का नॉर्म क्या होगा? वी वन इनर प्रोडक्ट विद वी वन इटसेल्फ। ठीक है, तो वन इंटू वन क्या हो जाएगा? वन इंटू वन वन डी टी, तो ये t का इंटीग्रेशन माइनस वन से ये माइनस वन से वन तक, तो दिस वुड बी टू। अब ये स्क्वायर था तो
Okay.
इसका वो लेंगे तो वन बाई टू। ऐसे ही अब x का क्या होगा? x इंटू एक्स टी स्क्वायर डी टी, तो ये हो जाएगा टी क्यूब बाई थ्री माइनस वन टू वन। ठीक है, सो दिस वुड बी वन बाई थ्री प्लस वन बाई थ्री, दैट इज टू बाई थ्री। तो ये क्या हो जाएगा? स्क्वायर रूट ऑफ टू बाई थ्री इंटू एक्स। ऐसे यू कैन फाइंड फॉर द लास्ट वन ऑल्सो। ठीक है, वो मैं छोड़ रहा हूँ। Okay, so this was about like last time I sort of rushed for this topic because of lack of time. This time I think that I have solved two questions in quite detail and it should be clear now. So now for the next half of this session, what I'll try to do is I'll try to solve very sort of elementary questions related to eigenvalue, eigenvectors, as well as some related to inner product spaces. Okay. So because these questions are elementary, so what I would want you to do is that you should attempt this question first, and then I'll try to go for it. Okay. So you can take a pen and paper with you and try to solve this thing. Okay. These are very sort of elementary questions, but sort of important questions because these are building blocks. Okay. So first of all, read the question. So the question is, let A be a given matrix, and eigenvalue of A is 2. So we are given that an eigenvalue of A is 2. Okay. So what it is asking is, it is asking you to find a basis for this corresponding eigenspace. So it is asking you to find linearly independent eigenvectors corresponding to lambda is equal to 2. Okay. So just a hint, so for eigenvalue lambda, so for eigenvalue lambda, any vector v satisfying this thing will belong to its eigenspace. Okay. So you need to find v satisfying this property. You know the A, you know lambda, identity matrix, you know, you need to find v. Okay. So give it a try, then I'll go. I'll wait for 2-3 minutes for you guys to solve. So how will we start? So like you got any answer or anything that could help me? Any you would have done 2-3 steps that I can skip and go straight away to that step. ठीक. So अगर हम लोग याद करें, so how we used to find an eigenvector? So we have lambda to be 2, right?
Sir, when put value of lambda is then matrix is 2 minus 1 6 um, R1 R2 R3 elements are same.
Yeah. So you want this into some
So
v1.
two rows.
Mm-hmm. Two rows would become 0, right?
Yes, sir.
So this is
Yeah.
2 minus 1
Then
6 0 0.
v1 minus V2 minus 6V3 equal to 0.
Yeah. So you get 2v1 minus v2 plus 6v3 is equal to 0. So now one
Yes,
thing
sir.
that you should remember is you have three variables over here, right? And
Okay.
you
Yes.
got only one condition, right? So when you row reduced everything, then you got one, you call it equation, I'll call it a condition. Okay. So you have 3 minus number of conditions or the number of equation that you get as your free variables, right? So, or you, other words, you can say the number of zero rows that you have are your free variables, right? So you have two free variables over here, okay? So what
Yes,
would
sir.
be the dimension of eigenspace?
Any value.
Uh, yeah, so the dimension of eigenspace would be 2. So you will have two linearly independent
Yes, sir.
vectors, okay? Why? Because you have two free variables. Dimension is nothing but number of free variables or the number of choices that you have, okay? Would be 2. अब कैसे निकालेंगे हम लोग यहाँ से this from here onwards it is very easy to like pick the eigenvectors, ठीक है? अब हम लोगों ने क्या देखा that we have two free variables, ठीक है? तो हम अपनी मर्जी से वो फ्री वेरिएबल्स कौन से होंगे वो चुन सकते हैं, कुछ भी चुन सकते हैं, इन तीनों में से किसी भी दो को फ्री मान सकते हैं और किसी भी एक को डिपेंडेंट मान सकते हैं, ठीक है? फ्री वेरिएबल्स और इंडिपेंडेंट वेरिएबल कुछ भी बोल सकते हैं, ठीक है? तो लेट्स से मैंने v1 और v2 को फ्री वेरिएबल चुना, यू कैन पिक एनी टू आउट ऑफ दिस थ्री, ओके? तो फिर क्या करेंगे हम लोग, लेट्स से हमने सबसे पहले बार में v1 को 1 लिया, ठीक है, और v2 को 0 लिया। तो हम लोग मान लो जो भी फ्री वेरिएबल सेलेक्ट करते हैं उसमें से पहले वाले को कुछ मान लेते हैं और बाकी सबको 0 कर देते हैं कैलकुलेशन आसान बनाने के लिए, ठीक है? तो क्या होगा, तो ये होगा 2v1 माइनस 0 प्लस 6v3 इज इक्वल टू 0। v1 में क्या है वैल्यू 1, तो यहाँ से v3 क्या आ जाएगा -2/6 दैट इज -1/3, ओके? तो एक वेक्टर हम लोग का क्या बन गया 1, 0, 1 -1/3। अब दूसरा वेक्टर लीनियरली इंडिपेंडेंट निकालने के लिए हम लोग क्या करेंगे, इस बार ही हम लोग v1 को 0 ले लेंगे एंड विल टेक v2 एज 1, okay? So then what we will obtain is that your 0 minus 1 plus 6v3 is 0, or this would imply that your v3 is 1/6, okay? So what is the second vector that you obtained? So the second vector that you obtained is your 0, 1, 1/6. So your eigenspace is span of these two vectors, 1, 0, -1/3 and 0, 1, 1/6, okay? Was it clear to everyone? Okay. Okay. So I want you to tell me the eigenvalues for A and B. What would be the eigenvalues for this these two matrices? So I have told this before. So if you have a, let's say, a lower diagonal matrix or an upper triangular matrix, then your diagonal entries are your eigenvalues, okay? You need not even calculate because when you will take determinant, everything rest will become 0.
302414.
Yeah. So for this one, your eigenvalues are 3, 0, and 2. And for this one, your eigenvalues are 4, 1, 4. Okay, so that's why I sort of included this question. There it is. Find it. Yeah. So now you need to check. These are three sort of related questions. That is 5 an eigenvalue for this particular matrix? And how would you check is, you will try to find an eigenvector for lambda is equal to 5. If you are able to find, then it is an eigenvalue. If you are not able to find, then it's not an eigenvalue. Similar to the last to last example where we found eigenvector corresponding to lambda is equal to 2. Over here, you have to find eigenvalue corresponding to lambda is equal to 5. So try this one. Then we'll go to the second question.
அது உங்க சாரா சார் சார் இங்க பாருங்க சார்.
Okay, so we will do the same thing again. Okay, so we'll try to look at the matrix A minus 5 pi. What is that matrix? This was the first question. Okay, so it would be 1 minus 3, 1. This is 3 minus 5, and this is 5. This is 2, 2, 1. So did you row reduce this matrix? So we want A into 5V is equal to 0. And we want V to be non-zero. Okay.
Sir, not 5 is eigenvalue of A.
So what you row reduced and it was full rank. What was the row reduction that you obtained? Like how did you reach to this conclusion?
First of all, I make lower triangular, upper triangular matrix. Then element is 6 minus 3, 1, 0, 3, 9, 0, 0, 44.
Okay, so you converted this matrix to your
Upper triangular form.
but that is not very valid, because if you have a matrix A, okay, if you do elementary row operation on it, then you can change its eigenvalues and eigenvectors. Okay, so your eigenvalues and eigenvectors are not preserved under elementary row operation. When you take A minus lambda I, then you can do elementary row operation. I'll give you an example. Let's say you have a matrix like this. Wait. What are its eigenvalues? So this is very easy. This is 1, 1. Okay. But if you now do this row operation, okay, and you sort of change this thing to this thing, that is your 1 minus 1 probably over here, and 1 0, And I think you can change it. Yeah, other way
The
around also.
determinant of lambda ai no a minus lambda I not equal to 0, so not 5
Then
is
it is
eigenvalue of
then
given.
it is not an eigenvalue. So what is the determinant that you got for this matrix? What is determinant of a minus 5 I that you got?
Minus 10.
Okay, I'll sort of believe that you got minus 10. So if you get this determinant to be non-zero, then that lambda is not an eigenvalue, not an eigenvalue. Okay. Okay, we'll go to the second question. It is saying that, let's say x is an eigenvector of A corresponding to lambda, right? So x is an eigenvector corresponding to the eigenvalue lambda. Then what is A3 of x? It is asking. What it is? Tell me. So A3 of x is nothing but something like
A
this.
square x 15.
So if x is your eigenvector with corresponding eigenvalue lambda, then Ax is lambda x, right? Again, you can write it in form
Yes.
A lambda x. What it, this is A of lambda square x. This is lambda cube of x. So if you have x as an eigenvector, then A to the power n of x is nothing but lambda to the power n of x.
Okay, yes.
Okay, so okay, read this question. Now suppose that b1 and b2 are eigenvectors corresponding to distinct eigenvalues lambda 1 and lambda 2. So for your lambda 1, you have b1, for lambda 2, you have b2, and for lambda 3, you have two linearly independent eigenvectors, that is b3 and b4, and these two are also linearly independent. It is asking if we write this all these vectors in a combined form, whether this set that we would obtain is linearly independent or not. Okay. So a few things that we have done in past is like, let's say you have distinct eigenvalues, that is lambda 1, lambda 2, and you have 1 eigenvectors corresponding to every one. So let's say for lambda 1 you had b1, for lambda 2 you had b2, and for lambda 3 you had only b3 and not b4. Okay. Then because this eigenvectors comes from distinct eigenvalues, then your set b1, b2 and b3 would be linearly independent. Okay, this thing we have done. Also we have done is, also right now we know that this b3 and b4 are actually linearly independent, right? Now the question is, like, if you combine both these things, whether it would be linearly independent or not. Okay, so we have to see this. I feel that it should be linearly independent set, and we will, like, if we have to prove, we can use the same way. Yes, you are saying something. Oh. So we can use the same way that we use to prove that distinct eigenvectors coming from distinct eigenvalues are indeed linearly independent. Okay. Okay, let's try this. So we are given that, okay, whatever we are given, we have written it above. So let's say we have C1 B1 plus C2 B2 plus C3 B3 plus C4 B4 to be 0. Okay. Now, if we multiply or operate on both side a minus lambda 3 I. Okay. What we are doing is we are multiplying both side by a minus lambda 3I. Why I am doing this is, if I multiply these two terms b3 and b4 by this thing, I'm hoping that it should become 0. Now, if my more and more terms are gone, then I'll have lesser terms to deal with, and then I'll be able to make them 0. Okay. So if we operate this thing on both sides, what I'll obtain is a minus lambda 3 times c1 b1 plus a minus lambda 3 times c2 b2 plus a minus 3 times c3 b3 plus a minus lambda 3 times c4 b4. This is equal to 0. Now, if you take this thing inside, then a into b1 would be lambda 1 b1, and this is minus c1 lambda 3 b1. Okay. Again, over here also you will have similar breaker. So this would be c2 lambda 2 b2 minus c2 lambda 3 b2. Over here, because you will have, okay, I'll write one term. So this would be c3 lambda 3 b3 minus c3 lambda 3 b3. These two cancel out to become 0, and the next term will also become 0, is equal to 0. So what we are left with is c1 times lambda 1 minus lambda 2 into b1 plus c2 times lambda 2, this is lambda 3 times b2 is equal to 0. Now you know that your b1 and b2 are coming from distinct eigenvalues. Okay, so these are linearly independent. Okay, because they are linearly independent, so if you take this quantity to be, let's say, alpha 1 and this quantity completely to be alpha 2, then your alpha 1 and alpha 2, this is alpha 1, this is alpha 2, then your alpha 1 and alpha 2 must be 0. Okay, so what does this mean? That c1 times lambda 1 minus lambda 3 is 0, and c2 times lambda 2 minus lambda 3 is 0. Now, as you know that your lambdas are distinct, lambda 1, lambda 2 and lambda 3 are distinct, so only option for this to become 0 is that your c1 is 0 and your c2 is 0. Okay, so you are done that you have your c1 and c2 as 0. Let's put it back into this particular equation. Okay, so the first two terms become 0, so you have 0 plus 0 plus c3 b3 plus c4 b4 is equal to 0. Now, as it is already given that b3 and b4 are linearly independent, so this would implies that my c3 is also equal to c4 is equal to 0. Okay, so hence this kind of combination also leads to linearly independent sets. Was it clear? Any doubt in this?
Hello.
Hello.
Sir, you apply a minus lambda 3 multiply by on to both side.
On both sides, yes. So this was my equation, and then I multiplied by a minus lambda 3i on both sides. So right hand side was 0 only, so right hand side would remain 0 only.
But second line equation a
minus lambda 3, so this is identity now, so we can just sort of
okay.
ignore. I is identity.
I understand, but a minus lambda 3 into c1 b1, then a c1 b1.
So this is a c1 b1. C1 is your constant, so this can come out. B1 minus lambda 3 is your constant, C1 is your constant, I into B1. So A into B1 becomes lambda 1 into b1, because b1 is an eigenvector corresponding to eigenvalue lambda 1. And this is identity into b1 remains b1. So this is how we
Yeah.
split this. Is it clear now? Okay. So, okay. So you have to attempt these questions. I'll give you some time to read and attempt, then I'll try to solve this. So for 24, you have to construct a 2 cross 2 matrix with only one distinct eigenvalue. Okay, so the distinct eigenvalue should be only one. You need to come up with such matrix. I'll wait till 7:13 for this particular question, that you need to construct a 2 cross 2 matrix which has only one distinct eigenvalue. Okay, so the hint is that try to construct a upper triangular, lower triangular matrix. Then you know certainly like what are its uh, eigenvalues, right? So for the diagonal entries, you keep the same number as for every diagonal element. Then you will have only one distinct eigenvalue, right? So if you construct something like 1, 2, 1, and 0 over here, then what are the eigenvalues? 1, comma 1. How many distinct eigenvalues? Only one. So this example is done. Okay, this is next question. It is saying, let lambda be an eigenvalue of an invertible matrix A. Show that lambda inverse is an eigenvalue for A inverse. Okay. So what you need to prove is, for 25th, you need to prove that A minus lambda times of some V is 1 by lambda V. Okay, and you are given that Ax is equal to lambda x. You need to prove this thing. Okay, so we don't know what V we should take. So let's try first of all with x. Okay, what if my x is the eigenvector for A inverse also? Okay, so let's put x over here. So what is A inverse of x? We need to calculate this thing, right? Let's say that this is, okay, we need to calculate A inverse of x, correct? And we know A inverse of x is my question mark, and we know that Ax is equal to lambda x. Okay. If I pre-multiply this thing, okay, with A inverse, pre-multiply with A inverse, what can we obtain is A inverse into AX is equal to A into lambda x. Sorry, A inverse into lambda x. A into A inverse is identity times x is lambda into A inverse x, right? So what is this? This is x is equal to lambda A inverse x. If you take lambda this side, this becomes A inverse x is equal to 1 by
X
lambda
by
times
lambda.
x, right? Yeah. So what does this mean? That if A has eigenvalue lambda and corresponding eigenvector x, then A inverse has 1 by lambda as its eigenvalue for the same eigenvector x. Okay. One more thing that I have not included here, but you should remember is that your A and A transpose have same set of eigenvalues.
Yes, sir. Uh,
Okay. Okay. Let's try 26th question. You need to prove that your A square.
Hello, sir.
Hello.
Hello.
Mm-hmm.
Uh, Some doubt in a question.
What? Hello.
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 Uh, Before this lesson, I solved a question, but I did not reach to answer this question.
You solved what?
Hello.
Actually, your voice breaks while you speak.
Hello.
Now you are audible.
Uh, Sir, this question is the number of 3 by 3 non-singular matrices with 4 entries as 1 and all other entries as 0.
Okay, can you please repeat number of 4 by 4?
Number of 3 by 3
Mm-hmm.
uh, non-singular matrix
Mm-hmm.
with 4 entries
With 4 entries
as 1
as 1.
and all other entries as 0.
Hmm. So what you want is that you want uh, this number you want, right?
Yes.
Okay. See, for non-singular matrix, what you want its determinant to be? What?
Determinant of A not equal to 0.
Not equal to 0, right? So you should construct matrices so that your determinant is not equal to 0. Okay. And you have only 4 ones to
Okay.
fill, right? So one thing is that you should have at least uh, 1 in every row,
Yes, sir.
right? So now let's say you are starting to fill this thing, right? So if you are in first row, right, then you can fill in this 1 at any position. Okay.
Yes, sir.
First row mein you can place 1 at any of the 3 positions. So how many choices you
Yeah.
have? 3 choices.
Okay. Yes, sir.
Okay. Once you have fixed your position of 1 in first row, when you move to the second row, right, what you want generally is that it should be, let me think, not just below this thing. Otherwise, what will happen is that your column won't have any ones, right?
Yes, sir.
So, what you want is your every column should also have at least one non-zero element. Okay. So
Yes, sir.
so now if you take this thing as that you have 2 choices, and your third one then will have only one unique choice. That is your
Yes,
whatever
sir.
position is left out of it. Okay, into 1. Now for the fourth one, like if you have filled something like this, then you can place your fourth this element at any position. Like if you place it here, 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 does it matter?
No.
Okay. So how many choices would be left for that thing? I think 6 choices would be left for that.
Yes, sir.
So I think this should be the answer, that there are 36 such matrices. I'm not very sure. What is the answer? According to me, there should be 36
Sir,
such.
at least 7.
At least 7.
Sir, answer of this question is at least 7. Oh, yes.
But if we have 4, right, then I think you can make more than 7, right? So you have 1 0 0 0 1 0 0 1 1. This is invertible, right? Let's take
Yes, sir.
this combination only. Okay, 0 0 1. This is also invertible, right?
Yes.
If you just look at the row reduction, you can't reduce it further, right? So this is also done. So another one is your, I don't think it would be 36, it would be some less than 36, but it would be definitely more than 7. So this is 0 1. So one thing that you can see is, let's say you fix the diagonals, right? You took this as 1,
Yes,
okay,
sir.
and then how many places are left? 6 places are left, right?
Yes, sir.
Hmm. So you have 6 unique matrices from here.
Yes,
Is
sir.
this correct? Then you will have 6 unique matrices from here, right? So when you once you have fixed the diagonal, okay. Now let's say this entry became 0, right? And my uh, this entry became 1 and this entry became 0, okay. Now I need a 1 over here also, and say a 1 here, okay. Now if you have this kind of matrix, earlier what kind of matrix we had? Earlier we had something of form 1 comma 1 comma 1, and somewhere else we have placed our 1. Now this matrix is completely different from the previous matrix.
Yes, sir.
So now you have filled 6 places, right? How many are left? 3 places are left. This position, wait, this position is left to be filled, and this position is left to be filled, and we can fill like if we fill 1 over here, we will get one unique matrix. If we fill 1 over here, we will get another unique matrix. If we fill 1 over here, we'll get another unique matrix, right? So then we can again get 3 more unique matrix. So at least 9 I can think that at least 9 would be there. Do you agree with it? Hello?
Yes, sir.
So did you understand how I got this 6 at the first place? That if I placed 1 1 1 on the diagonals, okay, and if I place 1 anywhere else now, okay, only 1 1 I have to place, and I have 6 choices to place. So that matrix that I'll obtain will always be invertible. This thing you agree?
Yes, sir.
So we have 6 matrices by that method.
Yes.
And if I made these diagonals to be 0 now, and I placed 1 smartly so that every row has a 1 and every column has a 1, okay, then
Yes.
also this matrix is totally different from the 6 matrices that we constructed earlier, okay. So then we again get 3 more unique matrices, right? So at least 9 I can think, more I think we can construct. So the answer that you're talking about, at least 7. So at least 9 we can think. So that answer can be updated to at least 9, right? For the moment. Okay. I think we can do some more changes and get more matrices. Like this would be then a sort of a problem of more of counting rather than linear algebra. That is, if you, let's say, yeah.
Sir, exact number of non-singular matrix 36. Yeah.
No, I don't think it would be 36. It would be something less than 36 because there will be some repetitions. Okay. You can, what you can do is, let's say if we now change this diagonal to be 1 0 0. Okay, right? So if we change our diagonal to be 1 0 0, what we can do is we can place 1 over here for this row and 1 over here for this row. Now again, if we fill in anything,
Yes.
then again that would be an invertible matrix, right?
No. Live, Bobby. NPTEL. Hello.
So we will again obtain 4 matrices from here. And you can like, this is more of a like counting problem. You can change the diagonals and then again count and see how many more you will get. So again, if you make that value, let's take this as 0, then you can place 1 over here and 1 over here. Then again you have 4 places, right? These 4 places. And I think this is 0 0 1. Then you can place 1 over here, 1 over here. Then you get 4 places, right? Is there any other possible combination of diagonals that I have? So if I sum this thing, this is 6 plus 3 plus 4 plus 4. So this is 17 at least I am able to find. There can be 1 or 2 that I missed, but for now you can take at least 17 as a good answer. So which is much better than whatever you said, that at least 7. So at least 17 is what I can answer you for this question right now. Are you there?
Yes, sir.
So I think at least 17 should be a good answer for this question. Okay.
Yes, sir.
Okay. So we'll get back to the question number 26. Okay. So question number 26 says, show that if A square is a 0 matrix, then the only eigenvalue that A can have is 0. Okay. So if you just a second, somebody is joining. Yeah. If we go to question 26, what we are given is that our A square is 0. Okay. And what we have to prove is that all eigenvalues of A is 0. Any suggestions on how can we proceed with this proof? Any ideas or hint? Okay. Let's say lambda is an eigenvalue for A. Okay. So if lambda is my eigenvalue for A, then what relation this satisfies? That A into V is equal to lambda times V for some V which is not equal to 0. This is what is my definition for eigenvalue. Okay. Now, if we pre-multiply both sides, by A, then what we get? We get A square V is equal to A lambda V. Lambda is my scalar, it can come out. So what we obtain is that A square V is lambda square
0.
of V, right? Now A square is given to be 0. Okay, just a second. Yeah, A square is given to be 0 matrix, so 0 times V is my lambda square V. So this is further 0. Okay, now my V is non-zero, we know that. So what does that mean? That means my lambda square is 0 or lambda is 0. Okay, this is how we can prove this thing. Okay. Okay. These are again very sort of simplistic questions. I want you to quickly do it and tell me the answers for each and every part. So you need to find the characteristic polynomial for these matrices. What are the characteristic polynomial? This is this determinant of A minus lambda I, right, equal to 0. So if you don't write equal to 0, so this is actually your characteristic polynomial. You need to tell me this thing. So when you equate this particular thing to be 0, then you obtain something as your like you whatever values of lambdas you obtain are your eigenvalues. Okay. You can try. I can try the first one, but I want quick answers to
Sir,
that.
eigenvalue is 9 and minus 5.
I don't want the eigenvalues. I just want the characteristic polynomial.
The a square minus 14 minus 4a minus 45 equal to 0.
Can you please repeat?
A square minus 4a minus 45 equal to 0.
Minus 45 equal to 0. Is this correct? Can someone else try to solve and verify whether this is correct?
Sir, 45, no 55, 45.
For the first one, for this matrix, right? I'll also try to solve. 7, 7, 2 minus t. So if you talk about the polynomial, then you can ignore this equal to 0 over here. This is the polynomial. Okay. I'll also solve and confirm. Yeah, Omkar has also got the same answer, but he has got a plus 45 over here. Can you cross check both of you, like who is correct? So this is I think it should be minus 45 only. Yeah. Can you quickly calculate for all of them? I think you can calculate probably for the second one and then we'll move ahead. I included this question because I didn't wanted that like there are some who also don't know this, then it would be a problem. Just the second part and then we'll move ahead. Hello, whoever typed in the chat box.
Sir,
Sirisha.
Second question of the equation a square plus 3a plus 2.
Repeat.
Characteristics of equation of second question is a square plus 3a plus 2.
3a plus 2. Okay. Onkar is saying that it is minus 8a unit. Sirisha, you have something to say? You can type in the chat box or you can unmute yourself.
Sir, I think first option, lambda square minus 4 lambda minus 45.
Yeah, that one is
I
correct.
think first option is right answer.
Yeah. Now we are trying to solve the second one. So one of them has
Lambda
suggested.
square minus 3 lambda
Mm-hmm.
plus 2. Lambda square
Hmm.
minus
3
lambda square
lambda.
plus 3 lambda
Okay, plus 2.
plus 2.
Okay. So Onkar, I think there is some calculation mistake probably from your side. I'll just quickly look at it. So this is lambda square minus 4 and you get uh, from here plus 6 and you get
And
from here
third is a square minus 3a minus 40.
minus.
40.
Okay.
So fourth one,
Mm-hmm.
lambda square minus 11 lambda.
Mm-hmm. Just,
Minus six.
ju- just this much.
Lambda square minus 11 lambda
Hmm.
plus 18.
Okay. Okay. So this was easy, but I wanted to just uh, include it so that nobody misses on it. Okay.
Sir, a lambda square minus 11 lambda
Mm-hmm. Yes.
plus 20.
Plus 20 you are getting. Okay, there can be. Okay, I'll try to solve the fourth one where there is a confusion. So let's.
Sir, all these are problems posting in problem solving session, sir.
These are in problem solving session. But
Posting.
I can recommend you a book also because I have picked from various sources. But like if you want to practice this, David say Lay book on linear algebra have a lot of solved as well as unsolved examples of this level if you want to solve. If you want to go a bit higher for proofs, then you can go for Fredberg's book. That is also book. So once this session would be over, I'll be posting this in the problem solving session links that you see.
Sir, sir, small doubts.
Uh-huh.
Sir, first assignment, 2 questions are wrong, sir. Every person is posting 2 questions, sir, but not responding, sir.
See, like I am not the responsible TA, but the problem is not also that. The problem is that we don't know who the actual TA is for correcting those kind of things. That's why we are not, we are also helpless. We also know that there is some mistake in answer, but I think they will rectify this thing. Don't worry about that thing.
Sir,
And
proofs also submitted, sir, but no use, sir.
I know, but the problem is that we TAs who take the problem solving session, we actually don't have any idea like who are the official TA for this course. And Professor Rana has, I think, retired. So these are recordings from 2, 3 years back. So he is also not responding. So yeah, but I think that would be taken care while evaluating. Okay. So we will move to a slightly non-trivial example. So we are given a matrix, 3 cross 3 matrix. Okay. Now we need to find a diagonal matrix D and an invertible matrix P such that A can be written in form PD P inverse. Okay. So, mhm.
Sir, in this question, given P is a invertible matrix,
You have to find P such that it is an invertible matrix.
then such that A equal to PD P inverse, then P inverse equal to I.
But matrix multiplication, you can't skip the D in between, right?
Then equality of matrix A equal to D.
But matrix multiplication is not commutative, right?
Yeah.
In matrix multiplication, you can't do AB is equal to BA, right? This is not always true. So that's why you can't take this P on this side and make it inverse. Okay. So how do we approach this kind of question is, so I'll tell you how do we construct D. So actually the D matrix is such that its diagonal entries are your eigenvalues for this particular matrix A. Okay. And P is such that its columns are eigenvectors correspond. So if you are using this first element as your lambda 1, then this E1 is eigenvector corresponding to your lambda 1 and so on. Okay. If you write it in this form, then you get this kind of representation for your matrix A. Okay. So I'll try to do it quickly. Okay. So let's first of all try to evaluate A minus lambda I, determinant is equal to 0. You can also confirm if you get the eigenvalues so that I can also match. This is right. This is same as 1 minus lambda 3 3 0 3 minus 2 minus lambda. I'm just doing R2 goes to R2 plus R3, and this would become minus 2 minus lambda. This is 3, this is 1 minus lambda. Okay. Okay, I think now we should just break this thing. You can tell me what are the eigenvalues. I will use a shortcut. Now matrix is 1 3 3. Anybody got the eigenvalues? 133 minus 3 minus 5 minus 3 and 331. Anybody got? Onkar, I don't think minus 5, 4, minus 2 is correct set of eigenvalues. The answer that you should actually be getting is 1, minus 2 and minus 2. You can look at your calculation. This must be some calculation mistake there. 133 minus 3 minus 3. Yeah, it should be 1 minus 2 minus 2. Okay, and the last one is plus 3 times 2 of this would become 0 because this is 3 times minus 2 minus lambda minus same thing. This would just become 0, I guess. Okay. It's lambda. If you take 2 plus lambda common from here, you get lambda minus 1 plus 3, and then you get 1 minus lambda, 2 plus lambda into 2 plus lambda. So the eigenvalues that you get is lambda is equal to 1, comma minus 2, comma minus 2. Now you have obtained your matrix D. What would be your matrix D? D would be 1, 0, 0, 0 minus 2, 0, 0, 0 minus 2. Okay. And in order to obtain matrix P, we need to find eigenvectors. So let's find eigenvector. To lambda is equal to 1. So it would be, what was the matrix? Let's sort of copy this matrix. Okay. Okay. So this matrix would become 0, 3, 3, this is minus 3, minus 6, minus 3, and this is 3, 3, 0. Okay. Times v1, v2, v3. We want this thing to be 0. Okay. Now we can convert. So what I'm doing is R2 goes to R2 plus R3. First step would be this. So they become 0, 0, 3, 3, minus 3, 3, 0, minus 3, 3. This is v1, v2, v3 is 0. Okay. Now I can add this one over here. So R2 goes to R2 plus R1, and what I obtain is 0, 3, 3, 0, 0, 0, 3, 3, 0, V1, V2, V3. So now using the first row, what condition you obtain is your V2 plus V3 is 0, and using the last one you obtain your V1 plus V2 is 0. So what does this give? This gives you V2 is minus V3 and V1 is minus V2. Now, as I said few moments ago in some other question, you have two independent equations over here. So now you have only one free variable. Okay. And you can choose that free variable to be anything of your choice. Let's say I take V1 to be my free variable. Okay. Then let's say I took my V1 to be 1. This would imply that my V2 is minus 1. V2 became minus 1. And from there, my V3 became 1 again. So an eigenvector is 1, minus 1, and 1 for lambda is equal to 1. Okay. Now we need to find eigenvectors corresponding to lambda is equal to minus 2. Okay. So for lambda is equal to minus 2, what matrix would I obtain? The matrix that I would obtain is 3, 3, 3 because I'm doing A minus lambda I, and lambda is minus 2. So this would be plus 2i. This would be minus 3, minus 3, minus 3, 3, 3, and 3. This is the matrix that I obtain. Okay. So this time some V1, V2, V3 is 0. This would imply, so you can straight away see that you can make this thing 0. You can make this thing 0, right? So only thing that is left is that V1 plus V2 plus V3 is equal to 0. Now how many independent equation you have is 1. Okay. So you have two free variables. Okay. So let's say I take it of my choice. Let's say I take V2 and V3 to be my free variables. Okay. So for the first time I take my V2 to be 1 and V3 to be 0. This would mean V1 is minus 1. And if I take Vt to be 0 and V3 to be 1, in that case also V1 is minus 1. So what are my two linearly independent vectors? So I get first vector as minus 1, 1, 0, and second vector as minus 1, 0, 1 for lambda is equal to 2. So how can I construct my matrix P now? I just need to write these eigenvectors in form of a column. So what is my first column? That is corresponding to lambda is equal to 1. So this is 1 minus 1, 1. And the other two columns are corresponding to 1, 1, 0, minus 1, 0, 1. So this is the P that you get, and D I have already written. It is 1, 0, 0, 0, minus 2, 0, 0, 0, minus 2. Okay. So this is how we can obtain P and D. So like I have seen the week 8 content also, whatever is taught till now, and I think initially we have already covered those kind of things, and exams are also coming. So next week what I plan to do is that I'll post post on discussion forum, and I'll ask everyone to like give their doubts, but I'm not sure many people would do that. So I'll try to do a sort of recap or a summary kind of a thing of whatever we did. I'll try to frame it so that I can fit it in 2 hours, and I'll try to solve some important question from every type, or yeah, I'll try to do that. One question that sort of addresses all concept in that particular topic, and it would be more of a like a doubt clearing session, like because this is that would be the last session for this course. I want, like, if you have any doubt or any topic that you have not understood, you can just post it in that forum, and I'll be also better prepared to address that issue then. So I'll try to post in discussion forum, and we will meet probably the next week for the last time. Uh, like whoever are here, anybody want to ask anything from today's content? Okay, then probably I'll end this session for today. And thank you everyone for joining this session.